Hey everybody. Today we're officially defining the definite integral. This is one of the most important concepts in all of calculus. Here's the official definition. We aren't going to dwell on it too much because it's pretty messy, but it's important to have some inkling for the machinery that lies beneath this definite integral as we start doing calculations in the future. We start with an interval, a comma b, and a function, f of x, that's defined throughout that interval. We then divide that interval into n subintervals of equal width, and we pick sample points in each of those subintervals, which we'll call x1 star, x2 star, and so on. The definite integral of f of x from x equals a to x equals b is just given by the limit as n goes to infinity, the sum k equals 1 to n, f of x sub k star times delta x, where delta x is b minus a over n, the width of each of those subintervals. Of course, this is only defined if that limit exists. And moreover, it's only defined if that sum on the right is always the same regardless of your choices for the xk star. By the way, that summation itself is called a Riemann sum. One useful fact potentially in undergraduate calculus is that if f of x is integrable, that is, if that limit on that right-hand side exists, on the interval a comma b, then it's always sufficient to use right-hand endpoints as the sample points. So the definite integral can be written, limit as n goes to infinity, k equals 1 to n, f of a plus k delta x times delta x. And if you've seen my video on the area beneath the curve, that definition is going to look familiar. Which brings us to this point. We frequently interpret the definite integral as the signed area between the graph y equals f of x and the x-axis. That is, the area beneath the curve. So, for instance, for this function y equals f of x, the integral from 1 to 4 f of x dx is a1 minus a2, the area above the x-axis minus the area below the x-axis. When you're evaluating the definite integral from a to b f of x dx, you should keep this picture in mind. At every x value, you're picturing a mini rectangle, something very, very thin. Its width is going to be dx, and its height is going to be f of x at that x value. So length times width, the area of the rectangle, is going to be f of x dx. So when you see the integral from a to b f of x dx, you want to think of that integral sign as adding up the areas of all those rectangles. The notation for that integral sign is actually just a stylized s. It stands for sum. It's literally doing this Riemann sum with a limit for you. Sometimes we can evaluate definite integrals just by using geometry, as in this case. Integral from 0 to 6, 1/2 x minus 2 dx. Here's the picture. I've drawn the graph y equals 1/2 x minus 2 on the interval 0 to 6. Of course, this is just a straight line with slope 1/2 and y-intercept of -2. So to compute that definite integral, I'm going to find the area a2 that lies above the x-axis, and then subtract off the area a1 that lies below the x-axis. These are both triangles, and I find the area of each one using 1/2 base times height. Overall, I get 1 minus 4, or -3. Here's another example. Integral from -2 to 2, square root of 4 minus x squared dx. This region is a semicircle of radius 2, so we can use the formula 1/2 pi r squared. Plugging in 2 for r, we get 2 pi.